imagine I've got some sort of XY coordinate system here. And I have some sort of linear material floating along the x-axis. The linear material here we assume has a uniform linear density, mu, which is just mass divided by length, or in our case right here, since it's uniform, that should also be equal to the differential of dm dl, or since our length is in the x direction, dm dx. Now, if we put a pulse in it, in this rope, moving at some speed v in the x direction, so this is dx dt, which is a constant. And if we look at a particular point on here, this thing is moving up and down. So at this point, this one's moving down, and there's one over here that decides moving up as this proceeds to go in that direction. And if we actually just expand on that right there, it's an incredibly tiny little bit of rope there of mass dm. This is some angle theta, and so we have some tension here on that side, and on this side we have just a small bit of tension in addition to that, so it's the tension plus some small differential of the tension, and the angle here is theta plus some differential of the angle. That angle there is theta. Now there's not a whole lot of difference between that, so if I sort of looked at this as sort of extend that the slope at this point, we have dy and dx. If we sort of extrapolate, this right here is incredibly tiny, so that basically would be the differential of a differential, so that is negligible as far as what our approximation here is going to be. So we've pulled a couple of pieces of information out of this. One important thing that we've pulled out of it is that the tangent of this angle theta is going to be equal to dy dx. So theta is equal to the arctan of dy dx. And in essence, we have this triangle here. Sort of expand that triangle out or make it bigger. Dy dx, and the hypotenuse is dx squared plus dy squared. And so some pieces of information that we will need later. I do want to point out that if y is equal to the arctan of a, then dy dx is equal to 1 over 1 plus a squared times dA dx. So from here, we now know that then d theta dx is equal to 1 over 1 plus dy over dx squared times ddx of dy dx. And so this becomes 1 over 1 plus dy dx squared times d squared y dx squared. That is something that we will need in a bit. Another piece of information from this triangle is that the cosine of theta is equal to the adjacent over the hypotenuse, so that's dx over the square root of dx squared plus dy squared. And that will come in handy later. So now let's come up with our equations of motion. I know that the acceleration in the horizontal direction is 0, so my sort of x equation is I have this force times the horizontal component of that force, which is the tension, plus my differential of the tension, times the cosine of that angle, theta plus d theta, minus the force in that direction, so that's just the tension times the cosine of theta, is equal to mass times the acceleration in that direction, which is 0. And then my y equation, my vertical equation, is I have this force acting upwards, so I have tension plus dft times the sine of theta plus d theta, minus the tension downwards, the component of the tension downwards, which is ft sine theta, is equal to mass, our mass, which is dm, times the acceleration in the y direction, which is dm times d squared y dt squared. I do want to point out since the bits of the rope are only moving up or down, but the uniform linear density, the amount of mass we have in the x direction doesn't change, because even if it stretches, so if we're looking at this piece right here, it had the exact same mass down here. I mean, it's spread out over a longer length here. However, in the x direction, it's still just as much length as it was before. Doesn't matter how much you stretch it that way, the linear density is still the same in the x direction. All right, so now we have these two equations. We need to expand those out. So if I take a cosine curve and I look at some particular some point on it, so this is theta and this is cosine of theta, let that point be theta there, and that would correspond to cosine of theta. This point right here is theta plus d theta, and so that point right there would be cosine of theta plus d theta. Now they're infinitesimally close to each other. I just can't draw them infinitesimally close, and so sort of go with the spirit of it. So I want to find the slope between those 2 points right there. And I know that the slope from algebra is rise over run, so let's just do change in y over change in x. Let's do change in the vertical over change in horizontal. So I have cosine of theta plus d theta minus cosine of theta over the change of these, which is theta plus d theta minus theta, is equal to, well, the derivative, because that's in essence what the slope is, the derivative of cosine of theta with respect to theta, which is just negative sine theta. My denominator here is just equal to d theta. And so if I multiply both sides by d theta, I get cosine of theta plus d theta minus cosine of theta equals negative sine theta d theta, or cosine of theta plus d theta is equal to cosine of theta minus sine theta d theta. If we do a similar type of outlook for the sine curve, we take the point right here. This is theta, so that's my theta axis and my sine of theta axis. I go out just a small little differential here of some infinitesimally small change in the angle, so this is theta plus d theta. That corresponds to sine of theta, and that corresponds to the sine of theta plus d theta. For you math purists, where I have a specific angle theta and I have a general angle theta here, and just in physics we get away with doing that because we understand what's going on there. In math class, they do not make that assumption, and so they throw a whole bunch of extra subscripts in there, which I'm not writing in the true spirit of physics. So going through a similar process here, so my slope between these 2 points is going to be equal to sine theta plus d theta minus sine of theta over theta plus d theta minus theta is equal to the derivative at that point, sine theta over d theta, which is cosine of theta. Again, my denominator here equals d theta. So I multiply both sides by d theta, add sine, and I end up with a sine of theta plus d theta equals sine of theta, when I add that over, plus cosine theta d theta. And so now I have enough to go plug into there. So let's do it. So I'm going to take my formula here for cosine of theta plus d theta, and then I'll take my formula for sine of theta d theta, plug it into that. So my x equation becomes my tension plus my differential of my tension times cosine of theta minus sine theta d theta minus tension cosine theta is equal to 0. And my y equation becomes ft plus dft times sine of theta plus cosine theta d theta minus tension sine theta is equal to my differential of my mass times my acceleration dy squared dt squared. I'm going to go ahead and FOIL out this, and let's just take a look at this one equation right here. We'll do this second, but so we'll do this one first. So doing FOIL, I have ft cosine theta minus ft sine theta d theta plus cosine theta dft minus sine theta d theta dft. So that is the foiling of this minus my tension is equal to 0. Let's go ahead and deal with this first. So right off the bat, those are going to cancel. This right here, I have two differentials being multiplied together, so this is going to be approximately equal to 0, especially since you're multiplying by some number that's 1 at the greatest. And so what I'm left with is, I'm just going to change the order around, cosine of theta dft minus ft sine theta d theta equals 0. Or going ahead and adding that to the other side, cosine of theta dft equals ft sine theta d theta. So from this, solving for that, I have my differential of the tension is equal to the tension times the sine of theta over the cosine of theta d theta. We will come back to that. Now let's deal with this equation. FOIL it out. Tension times the sine of theta plus tension times the cosine of theta d theta plus sine of theta d ft plus cosine of theta d theta times the differential of the tension is equal to my tiny little mass times d squared y dt squared. And I did it again, minus ft sine theta. I left that part out. So that's my foiling there, minus ft sine theta. That is going to cancel out. This is approximately equal to 0. And what I'm left with is my tension times the cosine of theta d theta plus sine of theta dft is equal to dm d squared y dt squared. So now, substitution. I have a formula right here for dft, so I can just plug that into here. So I'm left with tension times the cosine of theta d theta plus sine of theta times tension sine theta over cosine theta d theta is equal to dm d squared y dt squared. On this side over here, what do I have in common? I have ft d theta on both terms, so I'm going to factor that out. So I have ft d theta. Ft d theta times cosine of theta plus sine squared theta over cosine theta. It's equal to that. This we get a common denominator, so this is the tension d theta times cosine squared theta plus sine squared theta over cosine theta, which is, well, that numerator is 1, so I get tension times d theta times 1 over cosine of theta times dm d squared equals dm times second derivative of y with respect to time. So now, I'm just rewriting that last equation down. So I have the tension times d theta times 1 over cosine of theta is equal to dm times d squared y dt squared. And now we bring in some stuff that we've done already. So I'm going to divide both sides by dx. So d theta dx, we did that on the very first page. There's our formula for d theta dx. So I have my tension times 1 over 1 plus dy over dx squared times d squared y dx squared times 1 over cosine of theta. Well, we actually dealt with that because there's our cosine of theta, so the 1 over is just the reciprocal. So that is the square root of dx squared plus dy squared over dx. So in case you miss it, this right here is that, and this right here is that. And that's equal to dm over dx, d squared y dt squared. Now, if I factor a dx out of this, I get tension times 1 over 1 plus dy over dx squared times d squared y dx squared times dx square root of 1 plus dy over dx squared over dx. Dx is cancel. That's going to cancel out with some of that, so I'm left with, which is just the tension times 1 over the square root of 1 plus dy over dx squared times d squared y dx squared is equal to our linear density times d squared y dt squared. That is just the cosine of theta. Is the cosine of theta. If we factor the dx there, they would cancel out. So this becomes the tension times the cosine of theta, d squared y dx squared is equal to mu d squared y dt squared. If we divide both sides by this, I get tension. Actually, let's go ahead and bring mu over to the other side. So we're going to sort of flop sides there. So ft cosine theta over mu is equal to d squared y dt squared times dx squared d squared y. Those cancel out. What I'm left with is dx squared over dt squared, which is dx over dt squared, which is just the speed of the wave in the x direction squared. And so my speed of that particle, because remember, we're ultimately finding the speed of this bit of string right here, is equal to the tension times the cosine of theta over mu square root. Now, the speed of the wave, though, deals with this point right here. How fast is the wave moving at the peak here? Because this has some speeds in two different directions. So we really care about this when we can eliminate any possibility of dy dt. And so that is at the peak. So when theta is equal to 0, because at the peak, we're dealing with, well, theta gets smaller the closer you get to the top. So the angle is 0. Cosine of 0 is 1, and what we're left with is the square root of tension over the linear density. And that is yet one more way of deriving that equation.